Hi, today I'm going to show you a hack on a electrical filter that's often used in radio circuits. This is what is commonly called a double pie, meaning it looks like a pie, but there are two of them stacked one after another. I'm going to show you why this thing is pretty pervasive. You often would know that the middle capacitor here has twice the value of the two capacitors at the end. And I'm going to show you how that thing works. And then I'm going to go into some special cases where you can modify this one by adding a serial resonant capacitor or a parallel resonant capacitor to suit special purposes. Okay, so first let's go into this analysis here. I'm not going to waste a lot of your time. You can pause the video and look at the math. It's pretty simple, straightforward. The bottom line is, after you calculate it out, you will find that the impedance looking into a single pi is equal to L over C times Z, which is the load at the output side of the pi filter. From a unit point of view, this makes sense because L has a unit of ohm, 1 over C has a unit of ohm, so you have ohm times ohm divided by Z, which is has a unit of ohm, so the end result is ohm. Okay, so now let's go back and then look at why this thing behaves the way it is, like that. So when you stack these two pi circuits together, the first time when you look into, you have L over C times Z. When you look at it from the second pi, the Z in is also L over C times Z prime, which is the impedance looking into here. But since Z prime is equal to 1 over L times Z, so Z in now becomes Z. Okay, so that's the magical thing about this thing, which is why you see C to C, C. I would note that this happens exactly when LC resonates, at the frequency where LC resonates, right? That is when LC omega squared equal 1. All right, so normally this one is used as a low pass filter at the frequency of interest, omega. Z in looks like Z, so no change in impedance. At higher frequency, these capacitors will bypass energies. So basically, Z will receive little or no energy. And then at low frequency, L becomes negligible. So then again, this one would become just a Z. Now, another way to look at this one is to use XL as a impedance, which represent this component here, and XC, and so on. So you can calculate this again just using the same method, because I want to show that as long as this one is equal to the minus of this one, meaning L and C resonant, regardless of what is actually in here, right? Like this case, the thing that we just talked about still holds true. And I talk about the two special cases here. XL, there's L and C in series. This is the case. And the second special case is when L and C prime are in parallel resonant. So again, the same sort of calculation. I'm not going to waste your time. Take a look at this thing at your leisure time. So what it means is, for the special cases, the first one, since you put in a capacitor in the path, it is no longer a low-pass filter. So when you approach the low end of the frequency, you're going to see capacitor here, and then also these capacitors. So this becomes sort of like a voltage divider. So at the low end, it's going to approach some value that's somewhat proportional to whatever the values that you have chosen for C prime and C. Okay, so this becomes sort of like a bandpass filter, so to speak. And it is nice because sometimes not only that you want to cut down on the harmonics, but also some of the spurious signals below the frequency interest, especially useful at the output of a mixer. The other special case is when you have a tough harmonics that you cannot reduce appropriately, then you can add a paralleling C capacitors to this. As long as you chose that resonant frequency to be above your frequency of interest, then this parallel resonant circuit looks like an inductor to you. So this same double pi circuit still applies. Because of this resonant thing is going to block that frequency of interest, you can choose it so that it will sit directly on top of whatever the frequency that you want to get rid of, right? So that's it. That's a conclusion that you can modify a regular double pi filter by adding series capacitance or parallel capacitance to make it a bandpass or adding a notch. And by the way, this thing does not keep going down. It's going to go at a steady level. But you can pick that again based on whatever the values that you choose for C prime and C here. All right. Thank you. Bye-bye.